So welcome to the second session of this lesson. Here we are going to have an introduction, and again we are going to have a look at the basic vector algebra. And if you can recall about the Cartesian plane, we had two axes, the x-axis and the y-axis. We represented a point using Cartesian coordinates. So in other words, what you're referring to as a point here is a point as defined using Cartesian coordinates in the order pairs starting with x and y, defining where a line, for instance, starts within the Cartesian plane. For instance, you have a point P here that is defined by 2 points. It is defined by x and y. X a value along the x-axis and y a value along the y-axis. Their intersection is what makes up this point. We have Q, which is defined by the intersection of x, y, and z values, indicating that Q is three-dimensional. The Cartesian plane, of course, extends indefinitely. That's why we show it in mathematics having an arrow, showing that it is pointing to a certain direction and extending indefinitely. In computer graphics also, we'll discuss a lot to do with 2 dimensions and 3 dimensions. You note that there is a superscript here, T. T shows that P and Q are transposition vectors, meaning that they are column vectors. One is stacked on top of the other. We remind ourselves that vector quantities have both direction and magnitude. This is to differentiate them from what we call scalar quantities that only have magnitude and no direction. That has an impact when it comes to manipulation of vectors. Next, we look at basic algebra of vectors. So, just as you can perform basic operations such as addition, multiplication, etc. on scalar values, so we can also generalize such operations to vectors. And for instance, we can have vector addition. When we have two vectors, I'd like us also to note in the process how we are denoting the vector. In these diagrams, we have A, then with an underline, B with an underline, A with like that, to note that A is a vector. There are various notations which are used, and we should take note of them. So when you add in two vectors, we simply sum their elements at corresponding positions. So for a pair of 2D vectors, let's say A and B, where A has U and V and B has values S and T, we have A plus B, which are two vectors being added, equal to adding the element U and S, V plus T. In other words, adding the elements at corresponding positions. Same case for subtraction. Only that when you talk of vector subtraction, we have to know that we are negating the entire, so that the negative B means negative S and negative T, for instance. So if you are subtracting, if it is A minus B, meaning subtract vector B from vector A, that implies it is equivalent to A plus the negated B, which is equals to U minus S, V minus T. I think that makes sense. It's similar case to addition, only that is subtraction. Corresponding values once more. And we look at vector scaling. Scaling means that you are adding or multiplying by a certain factor for all the values. If we wish to increase or reduce a vector quantity by a scale factor, let's say lambda, then we multiply each element in the vector by lambda. Lambda can be any value, say 2, 3, of course 1 doesn't have any effect. So if, for instance, you want to scale vector A with a value, let's call it lambda, so therefore you have lambda A, we are going to have it is equivalent now of lambda U and lambda V. So that vector will be scaled up. If we want to manipulate the magnitude of a vector, or to obtain the magnitude of a vector, or to indicate the magnitude of a vector, we use the absolute sign. You know, the two pipe signs. If you are using a laptop to type, we write the length of the magnitude of a vector as S. Then these pipe signs. That means it's absolute, because sometimes vectors we have negative values, but the length shouldn't be negative, because it's, is a value that reflects the length of the vector. So independent of whether it's facing in whichever direction, it's still going to be the length is equal to this much. So the absolute. We use Pythagoras theorem to compute the magnitude, which then we compute as the square root of the sum of squares of the values in the values